Section 4.6, the multiplication rule and independence. The multiplication rule says if A and B are any two events, then the probability of A and B is the probability of A times the probability of B given A. Where did that come from? It actually came from the previous section. So if in the previous section we learned that the probability of B given A is the probability of A and B divided by the probability of A. This is over 1. If we cross-multiplying, if you remember, A over B equals C over D. The cross-multiplying A times D is equal to B times C. And that's what happened. Probability of A and B times 1 is the probability of A and B equals the probability of A times the probability of B given A. That's where this came from. So they are the same rule, but just interchanging. And how do we apply something like this? I showed you some examples in the previous section about this. Let's say we are given the probability of A is 0.8 and the probability of B given A is 0.4. We need to find the probability of A and B. To do that, we can apply the rule here. Probability of A and B is the probability of A times the probability of B given A. That would equal 0.8 times 0.4, which is 0.32. Straightforward formula. Now, what about if they give it to us as fractions? As another example, let the probability of A is 7 over 8. The probability of B given A is 5 over 7. You need to find the probability of A and B. Here I give it in a fraction form, not decimal form. To calculate the probability of A and B, we find the probability of, as you know, it's the probability of A. We don't have division. Just probability of A times the probability of B given A. Probability of A is 7 over 8. B given A 5 over 7. And notice you can cancel 7 with 7. That gives us 5 over 8. 5 over 8, which is 0.625. Now we introduce the independence. So independent events. We say A and B, or B is said to be independent of A, or the two events are independent if this condition is satisfied, that the probability of B given A is equal to the probability of B, And how do we apply this? Let's say, look at an example. Let's say we have 52 deck of cards, and we would like to find, so 52 deck card. Let's say we need to find the probability of getting a face card. Then we're gonna find whether the face card, this is the event, we're drawing a face card, independent of, or let's say a king. Find whether selecting a king is independent of selecting a face card. Let's see. To do that, we need to check. Let's assume the king is K and this is F for face. So to check, of course, for the first one, if we need to do the first one here, face card, how many face cards are there? in a standard deck of cards. There's 4 of them, or how many? How many face cards do we have? We have 12, right? 12 over the total. If you start reducing, let's say by 2, 6 by 2 is 26, by 2 again, 3 by 2, 13. And you can convert that to decimal if you like. Find whether a king is independent of face card. Like this event of withdrawing a king is independent of face card. To do that, we need to find the probability of a king given it's a face card. And we're gonna check if this is the same. Is this the same as if you take if you withdraw the probability? Because if you look at the definitions here, see, if the first one B, this goes in there. So king, so K goes in there. Are these two the same? Well, let's see. To find the probability of king given face means now how many given face means it already has occurred. It means we are taking out of 12 face cards. There's 12 of them, as I showed in the first part. And king, how many kings are there? There's only 4 kings. So that gives us 1/3, which is 0.333. What about the probability king, withdrawing a king? Withdrawing king, how many kings are there? There's 4. Over how many? 52. So this simplifies to 1 over 13, which is 0.077. They're not the same. The probability that K given F is not the same as the probability of K. So the two events are not independent. This is one of the best examples we use for independency. We can add to this part 3. Part 3, determine whether the king, taking a king, independent of a heart, withdrawing a heart. King withdrawing a heart. So the king, we called it K earlier. Heart, I'm gonna call it H, the first letter of the word heart. So what we need to do is we are going to find the probability of K given H and compare it to the probability of K. Compare it to the probability of K. So what's the probability of K given H? Probability of K given H. This means H has already occurred. So how many hearts are there? How many hearts are there? Well, there's 13 hearts, because each one of them 13. Now now from those 13 hearts, how many kings are there? There's only one king. Only one king. So that gives us 0.077. And the probability it's king, we just found it in the previous part. It was 1 over 13 again, 1 over 13, which is 0.077. So the two events are what? The two events are independent. The next thing, what happens if events are independent? Well, they call it the special multiplication rule here for two independent events. If A and B are independent, either given or we prove them, then the probability of A and B is equal. There's a missing equal. The probability of A times the probability of B. And the converse is true. So this means if the probability of A and B equals the probability of A times the probability of B, then the two events are independent. It helps us to find probabilities. So if we need to find, notice how we had the king, withdrawing a king, and heart are independent events. So if I want to find the probability of king and heart, you can say it's the probability of king times the probability of heart. So the probability of king, how many kings are there? There's 4 kings out of 52 times how many hearts? 13 out of 52. And then either multiply or simplify to get an answer. That doesn't work only for 2 events, but for n number of events, or you can just take the probability of A and B and C and is the probability of A times the probability of B times the probability of C. So that works no matter how many events we have. So if we look at an example in this given, A, B, and C independent events. And given the probability of A is 0.2, the probability of B is 0.4, the probability of C is 0.8. We can ask you to find the probability of A and B and C. Well, since they are independent, by the rule up there, it's the probability of A times the probability of B times the probability of C. So probability of A is given 0.2 times 0.4 times 0.8. And all we have to do, just multiply them out. Multiply all the 3 numbers out. 0.2 times 0.4 times 0.8. So that gives us 0.064. Final note here. Remember how in independent events we get that the probability of A and B is equal to the probability of A times the probability of B. In words, this is the joint probability. So we can say that the joint probability equals the product, see, it's the product of the marginal probabilities. See, these are this is a marginal probability, this is a marginal, so that's their product. Good to keep in mind.